uniform external magnetic field, or in other way we can say that it is a work done to rotate a dipole in a magnetic field. So first we'll do what is the work done to rotate. From there we will just find out the absolute energy of a dipole in a magnetic field, because in the last video we proved that the torque acting on a dipole is actually equal to mb, in vector form it is actually m cross b. In scalar form we can say that it is mb sine theta. The other thing you should know is work done by the external force is equal to negative of the work done by the dipole. So that means that if work is done by the system, its energy decreases. That is why usually when external work done is positive, work done on the dipole is actually positive, hence its energy increases. Usually the external work is done against the direction of the initial thing. That is why the negative of the work done by the dipole becomes the external work. So this we have often seen, and at least in so many places, in gravitation, in work energy, and then in electrostatics, in so many places we have seen about this. Okay, let me explain the situation. Suppose there is a uniform magnetic field exists in a region. So the uniform magnetic field is represented by parallel lines of force, magnetic lines of force. There is a bar magnet in this. This is the south of the magnet, this is the north of the magnet. Hence the dipole moment is from south pole to north pole. The angle between this magnetic moment and this magnetic field is the angle theta. So you know that the torque is always along the direction of the magnetic field, such that the north pole will tend to align itself. So I'll use a different color to represent this. So after some time what happens, the field will do the work so that the south is here, north is here. It will align itself in the direction of the magnetic field. So I'll just try to simply describe the situation. This is the direction of the magnetic field. This is the direction of the dipole m, and the angle between them, let us say it is theta. In this case, what is the torque acting on it? And before we find out the torque acting on it, if the dipole is rotated through a very small angle d theta, so the dipole will be like this. Assuming this distance as r, the small distance it moved, it's almost a straight line. If it is a small distance, let's say it is ds. Let's say this small angle moved as d theta, this small angle. So what is work done? So the amount of work done is actually force dot displacement. Here I am just multiplying. This is the displacement, this is r, this is the perpendicular distance. So the perpendicular distance here is r. Hence I am multiplying by r perpendicular and dividing by r perpendicular. So you know that if this is the angle, this is dl, and this is l, and this is theta. By the definition, if it is dl, it's a small distance, this angle is d theta. So d theta equal to this arc length dl by this perpendicular distance l. Similarly here, r perpendicular in tf represents torque, ds by r, which is perpendicular distance, which is d theta. So in rotating a dipole through a small angle d theta, work done is equal to tau dot d theta. So if you want to find out the total work done in rotating it, so from where to where you are supposed to rotate, suppose this is the direction of the field. Initially the dipole is in this direction, let's say the initial angle theta 1, and you are rotating this such that finally the dipole comes to this side and this final angle theta 2. So the work done to rotate this is integral from theta 1 angle to theta 2 angle tau dot d theta. Tau dot, because the total work done is integral of all small work done, which is tau d theta, which is mb sine theta d theta, theta 1 to theta 2. So here what you get is mb, we can take out integral sine theta d theta is minus cos theta and theta 1 to theta 2, and I am taking minus also out, minus mb into cos theta 2 minus cos theta 1. Now when you apply when you multiply this negative sign, so the work done in rotating a dipole is mb. Cos theta 2 is minus into minus plus, so I'm writing cos. Okay, I'll just do one step at a time. So when I multiply this, minus mb cos theta 2 minus into minus plus mb cos theta 1, which means that the total work done is mb into initial angle cos theta 1 minus cos theta 2. This is the work done. If you want to find out, because in a scale if you measure a distance from 3 centimeter to, let us say, 8 centimeter, the distance is actually 5 centimeter. Suppose in the same scale you go from 0 centimeter to find the difference between 5 centimeter. So the final minus initial, when you put here, final is 8, initial is 3, hence the difference you get 5. Suppose the final is 5, initial is 0, means the difference becomes the final value, right? In the same way, I'm just choosing this particular portion of the dipole. This is the magnetic field direction, this is the dipole direction. The angle between them is 90 degree. So the dipole has 0 energy, and because the external work done is energy of the dipole, so which is mb cos theta 1 minus cos theta 2. Suppose I'm just rotating the dipole from angle 90 degree to a particular angle theta. So the initial energy is actually 0. Here is where the final energy, usually the amount of work done or the change in energy, because whatever amount of work is done, that much energy will be either increased or decreased in the system. So the total difference in energy is this, the difference between the energy. So here I'm applying this condition here, delta u equal to u final minus u initial, that is given by the relation mb cos initial angle 90 degree minus final angle theta cos theta 2 becomes theta. So the amount of difference in energy becomes actual energy because initial energy is 0. So mb cos 90 degree becomes 0. So it is minus mb cos theta. So the energy of a dipole in a magnetic field is actually minus mb cos theta. So sometimes they'll ask amount of work done. So this, if you take it as a reference, it will be very easy for us to solve the problems. How is that? Suppose let's consider 3 positions of a dipole. This is the direction of the magnetic field, but the dipole is aligning itself in this direction. This is the direction of the dipole. The angle between the magnetic field and the dipole from here to here is 180. So energy of a dipole when it is anti-parallel, that is at 180 degree, equal to minus mb cos of 180 degree. Cos 180 degree is actually minus 1. So minus 1 into minus mb, that becomes plus mb. Plus mb, energy is 180 degree plus mb, so it has a positive energy. So when the dipole is in this direction, the torque acting on the dipole, which is mb sine 180 degree, sine 180 is 0, so this is 0. So the torque acting on this dipole is 0, but the energy is in positive. That means it is in unstable equilibrium. The moment you just slightly disturb the dipole from this orientation to this orientation, immediately this dipole tend to come into this. Suppose the dipole is in right angle to the field. So this is the field, this is the actually magnetic moment. The angle is 90 degree. As we have seen here, energy of a dipole at 90 degree equal to minus mb cos 0 degree. Cos 0 degree is 0. So and torque at this is mb sine 90 degree. the sine 90 is the maximum value of sine. So the torque acting on this dipole is mb. That means maximum. So at this position, energy is also at 180 degree position, energy is maximum. At this position, torque is maximum and energy is zero. Energy is zero. What if the dipole is aligned in the direction of the magnetic field? In the direction of the magnetic field, so the angle between the magnetic field and the magnetic moment is 0 degree. Hence, this is 0 degree. So in this case, energy of a dipole at 0 degree is minus mb cos 0 degree. Cos 0 degree is 1, hence it is minus mb. So that means that energy at 0 degree is actually negative. Because it is negative, it is stable. So at this case, energy is minimum and torque is equal to PE sine 0 degree. Sine 0 degree is 0, hence torque is 0. Energy is minimum, torque is 0, so this is in stable equilibrium. If you disturb the dipole slightly and leave, it will again come back to the original position. So when the dipole is anti-parallel to the magnetic field, when the dipole is anti-parallel to the magnetic field, its energy is maximum, hence it is an unstable equilibrium. What is unstable equilibrium? Unstable equilibrium is when you slightly disturb the system, it will go into a separate into a new position or new configuration. So here is the magnetic field, suppose this is the dipole. So in this case, if you slightly disturb the dipole will immediately move into this and align in the direction of the magnetic field. So it goes from this configuration to anti-parallel configuration to parallel configuration upon the slightest disturbance. That is why it is called unstable equilibrium. So in this case, it experiences a maximum torque in the direction of the dipole. And here in this case, its torque is 0 and energy is minimum. So because it is minimum, all systems in this universe try to attain as smallest or as least energy as possible. So this case, when the dipole is parallel to the magnetic field, it is in stable equilibrium.